So I wanted to also do an example, well, not an example, but a video on the work done by a spring. Part of the reason for that is because the spring is a varying force, so we have to actually calculate the work using an integral. But we're still going to come up with a really similar endpoint that we did with the work done by gravity, and we'll be able to see what the potential energy function is for a spring. So we're going to just imagine a horizontal spring on a surface. We're going to assume, of course, that this surface, that this mass on a spring is resting on is frictionless, so that we don't have to worry about friction interfering with our problem. I noted on the picture where the equilibrium position of the spring would be, and then we're imagining the spring moving from this point x initial to this point x final. It doesn't really matter if I'm stretching it or compressing it. When we see the final expression for potential energy, you'll see why that's true. Now, the force of a spring we learned in class is minus kx. Remember, k is the spring constant of the spring. It's a characteristic of the individual spring and indicates how hard it is to either stretch or compress it. The higher the value of k, the more stiff it is, and it also means that it's harder to stretch it or compress it. We're going to have to use the integral form of work because of the fact that the force varies with distance. Because the force is just a function of x, we can change our dot product to just the force in the x direction times dx will be take the place of ds. Now, we can put the minus sign out here, and so our integral is minus k, is just kx dx, and we're going to go from x initial to x final. And so when we integrate that, we get minus 1/2 kx squared, and we're going to evaluate it at the endpoints. And just like we did with gravity, we see that we actually have something that looks a lot like the change in the quantity, because we see that the work done only depends on where we started and where we ended. It doesn't say anything about what happened in between. In fact, this spring could have gone back and forth before it got back to x final. We don't know, and it doesn't really matter. If we take out the negative sign, then we get 1/2 kx final squared minus 1/2 kx initial squared. And so this is where we can deduce the expression for the potential energy of a spring is 1/2 kx squared, because then this makes this equal to minus the delta U of the spring. And so again, just like we had for gravity, there's a relationship between the work done by the spring and its change in potential energy. It's going to be the same in that in order for the work to be positive, the change in the potential energy of the spring will have to be negative, and then vice versa. So these are expressions that we're going to use quite frequently: the potential energy of a spring and the potential energy of gravity. And those will become really useful when we get into conservation of energy.